Hello, welcome to Triple E 117. This is Dr. Tracy Stoops. Here we're talking about network analysis. So here particularly we're in chapter 15 where we're talking about active filters in circuits. If you remember last time we talked about passive filters or filters of frequency selective circuits. Now we're talking about how to do the same task of selecting frequencies to let through with the additional benefit of having gain in the circuit. So you could increase the power, kind of like an amplifier for your audio or something like this. So first off, before we get really to the filtering part, we need to do a small review of what does active mean in like circuit analysis. Okay, we've always talked about passive elements. What's an active element? Okay, a passive element means there's no external power added to the circuit or the device, so you can never get a gain above one, meaning you can never add power into the system. You can never increase the power going out of the circuit because you have no source to draw power from, right? Filtering means only letting the select frequency signals through. So I could choose a group of signals, I'll let those through and block everything else. That's what a passive filter means. An active filter means that we connect external power to the circuit so we can increase the gain. So the power could be greater than one. So we could like power a laptop or big home audio speakers, something like this, right? So we're basically adding more power to the circuit to increase so we could power a bigger load. Okay. Obviously, we need external power supply to this. This is why you plug things into the 120 volt socket in your home, right? Because it helps amplify things. Okay. Again, the filtering part, that's just selecting the frequency you want to let through and blocking everything else out. Okay. So anytime we talk about an active circuit with a gain in circuit analysis, typically we go to something called an op amp or an operational amplifier. You've definitely seen the triangle before. You've seen it in Engineering 17 and your other circuits classes. Here we're going to do a review of it because this is a key component in the active filter. Okay, so each op amp will have various pins that you connect the power to inputs and outputs. So on a circuit diagram, it's typically a triangle where you have two inputs coming in. You have a positive input and a negative input. Okay, that's the input signal going into the op amp. You have external power, so the op amp will always have a positive power supply and a negative power supply. So you need to connect external power to these points, and that's the power it'll draw to have a bigger output. So maybe if we put 5 volts in and we want to get 50 volts out, the only way the output's going to have 50 volts is it needs to draw 50 volts from one of these external power supplies. So we need to make sure we put 50 volts on the V positive if we want an output of 50 volts. Okay. So external power will always be needed for op amp to amplify. Okay. So left hand side is input. In the middle, we have external power. On the right hand side, we have an output pin. This is the edge of the triangle. It comes out. This is typically we assume it's a positive terminal of the output. This confuses a couple people. Because there's no negative terminal with the output. It's only one pin. So how do you measure output voltage? We typically reference voltage to ground like this. So this output could be plus 50 volts. But what is that always referenced to? It's going to be referenced to the ground of the circuit. And the ground of the circuit will filter in from somewhere else in the circuit, in the circuit into the op amp as well. Okay. So right side op amp output with the ground as a reference. So you have a voltage difference to calculate. Okay. So that's the 3 stages you look at an op amp: input, the external power, and the output. Okay. Now, first off, how do we connect the op amp? The first thing you have to do is you need to connect the power supplies. Okay. You have input voltage and you have output voltage. So here on the bottom, you have this common node. This is typically your ground node, everything's connected to. So if I was in the lab and I was connecting things, we'd have an input voltage to the positive terminal of the input, and that's going to be referenced to ground. So there's an input signal coming in from the previous device or source. The negative terminal of the input will also have, it could have something in a circuit, and then that'll be referenced to the ground as well. So somewhere previous to the op amp in the previous circuit before, these devices were connected to ground and they kind of did their thing. It could be like a music player or some computer architecture device, something that had a ground before and did something, gave us a signal, and that's the input signal. Right? It could be like 5 volts, 2 volts, 3 volts, something, but there's an input signal coming into the op amp. Okay. So what terminals connect the input voltage? Source voltage V positive. This is from the previous circuit, goes to the positive terminal of the op amp input right here. Inside the triangle, that's the positive terminal. Negative voltage of the source goes into the negative voltage of the terminal as well. Okay, so whatever's coming in goes into these two terminals. You have your output voltage right here. That's connected output voltage, goes to this next part of your circuit. And then there's a ground reference for that as well. So remember, a filter is kind of like a middleman circuit where you have something coming in, it's getting changed, modified, and is spitting it out to the rest of the circuit. So we're just passing it through, we're just modifying the signal. Okay. Lastly, don't forget you got to put your source in. So here you have a DC source from a ground. Notice that the polarities are backwards, the positives to the ground and negatives to the V negative. That way we can have a negative voltage. So maybe the ground is 0 volts and we want our input to be plus or minus 50 volts. This will be a 50 volt source. VCC will be 50 volts. But because we're on the negative terminal, it'll go to negative 50. So V minus will be negative 50. This is the same 50 volt source going to the positive terminal. But notice that the V source has a VCC has a positive terminal going to the positive of the op amp, the positive source of the op amp. So this will be a positive 50 volts. So you can see the range of this op amp will be positive 50 and negative 50. That's the range we got amplified. Okay. It's very critical you got to connect these sources into the op amp, otherwise it's not going to work. Okay. So we have everything set up where we know how to connect it. So the big question is, what does an op amp do? Right? Obviously, it amplifies, right? But how exactly does it do it? Okay. We're not going to go to the exact internals of the port of the op amp because this is an electronics course, but there's a couple golden rules for op amps to remember. First off, the input voltage coming in, so the previous circuit has an input signal coming in, there's going to be 0 amps going through the circuit. So the input terminals typically have an infinite impedance, so you're not going to have current flowing through it. It's only going to sense voltage. Okay, so all we have to do is touch the input terminals with voltages. We don't necessarily have to send current through it. It's just a little tap of the voltage. And the reason why they do this is it's more power efficient. If we don't have current flowing through the op amp, it's not going to sap energy out the circuit. So we can't put a voltage on the terminals, but we don't put current through it. It just taps the voltage. The voltage, in my opinion, just taps the terminals just to say, hey, this is the voltage the circuit amplifies. Okay. So golden rule is no current flows on the input terminals of the op amp. Very, very important to understand. The output voltage here, V out, is going to try to follow the difference of the inputs. So the gain, V out, is equal to the gain times the positive voltage coming in minus the negative voltage coming in. So whatever the difference between these input terminals, it'll multiply that by a lot. Okay. So that's the whole point of an op amp, is taking the difference of the voltages, and then that gets amplified to a larger extent on the output. Okay. The gain itself for modern op amps are really, really high, like in the millions level. So typically when you have a voltage difference here, it's just going to shoot up to the positive or negative maximum we can do. Okay. Now, there are limits on what your output voltage can be. The output voltage, again, can never be higher than your positive supply, can be never be lower than your negative supply. So somewhere in the middle. Okay, so if this is positive negative 50 volts and my output voltage is 1,000 volts, calculation wise it'll be 1,000, but it'll realistically hit a maximum of 50 volts and never go higher. Okay, you can't just magically get more voltage than what it's gives you or op amp. Okay, so that's kind of the golden rules. is just remember, no current going into input. The difference of the input voltage will make V out much higher, and the maximums are the supply. That's it. I mean, that's all op amp is at the end of the day. It's just this a simple math calculation and spits out the answer. Okay. Now, the op amp alone, because it either goes to maximum, it goes really high or really low, there's no control in the middle, it doesn't really help us. So what we need to do is we need to make a circuit around the op amp to help control the op amp. Okay, so the op amp alone is not really that useful, but when we connect resistors here and put some sources here, then we can start using it as a tool and stabilizing the op amp to a circuit we can use. Okay, so this is a very typical inverting op amp circuit. I'm sure you've seen this in Engineering 17 before. We're going to go step by step to understand how the circuit works. Okay. First thing is let's look at the input. This is how I would analyze any op amp circuit I ever come across. Because right now it kind of looks like a mystery. I don't know what's going on. It's confusing. Okay. Again, as engineers, we have a step process of trying to understand things. And let's go step by step and take baby steps to figure everything out. First thing always is, what is the input voltage is doing? What's going into the op amp? So we know we have a voltage source coming in. It's going through the resistor. And it's going to hit the positive terminal here. So the positive voltage here is going into the negative terminal of the op amp. Okay, that's why it's called inverting, because the positive voltage is going into the negative voltage of the op amp. So naturally, the output voltage will be negative because we're putting into the wrong terminal. Okay, so something's happening in this negative terminal input. What about the positive terminal input? This is actually going straight to ground, 0 volts right here. So this is literally, again, we're making it easy. We're not going to put a second voltage source here. We're just going to plug this as 0 volt to ground. So V positive will always be 0 volts. And that helps kind of stabilize the op amp. Now remember, no current's going to flow into the circuit from here, right? There is an error that says IM, but that's 0 amps always. Okay. But note that we have a positive voltage on the negative terminal and 0 on the positive terminal. That's what we have to go with. The output here coming out is going to be whatever the op amp is going to do. It's going to increase the current voltage somehow, and we're going to get output voltage. And then it's going to be positive terminals across the output pin and negative terminals ground. Again, because it's inverting, the output will be negative. So this voltage in green right here will actually be like negative 15 or negative 20 volts. Okay. So that's what the, like I said, right, the inverting part means the output voltage will have the opposite polarity. Okay, so that's the two things coming in. We're just looking at what goes in and what goes out. Okay, so input stage, output stage. Now the question is, what happens in the middle? Why do we have this resistor in the middle? What does it do? Okay, this is a very classic example called a feedback loop, where we're taking the output voltage and feeding some of that current back to the input stage to give a feedback information. That way, the op amp can make a more informed decision because we're always feeding back what's going on. Okay, this is like a basic control loop. Now, we need to put a resistor here so we don't just blast 1,000,000 amps back in, right? We need to put some resistors to slow the current down. And so this resistor will help balance things out. Okay. And this is typically called RF, or called the feedback resistor. And we could tweak this resistor here to control the op amp. That's the whole point of this inverting op amp part. Okay. Now, one of the golden rules for this inverting op amp is, remember, this voltage. So we have 0 volts in the positive terminal right here. Okay. The gain of the circuit is really, really high. So it's going to try to stabilize the output voltage, not to be too high, not to be too low. It wants to keep it in between those VCC, the positive and negative sources. So the output voltage will do whatever it takes to send a little bit amount of current back through RF here toward this voltage on the negative terminal will also be 0 volts as well. If we can make both of these voltages equal to 0, the gain's not going to be too bad, and we're not going to make the op amp go to like positive infinity or something crazy like that. Okay. So one of the key components in inverting op amp is because we grounded the positive terminal 0 volts, the circuit is going to want to make the negative voltage, the negative input terminal 0 volts as well. So we want to make sure these two voltage terminals are the same. Okay, and the output voltage will do whatever it takes to force these two terminals to 0 volts. That's the key component of the inverting op amp. Now, let's build on that. I just said, look at these two terminals. We want to make sure these are 0 volts at all times. The positive terminal is 0 volts because it's grounded. What voltage is attached to the positive terminal? It's connected to ground. Ground is 0 volts. That's going to stay like that for the whole entire circuit. Okay. Now the negative terminal right here is connected to a resistor and another resistor. This voltage right here, V1, can change, right? Depending on how the circuit's set up. We want to, the op amp will force itself, the output voltage, to ensure that this V1 is equal to 0 volts. That's the feedback system. So maybe initially when it turned on, this might be 5 volts, and the op amp doesn't like that. The op amp wants to close the gap to make sure these are both 0. So this is 5 volts right here to begin with. The op amp will change its voltage to eventually make this go from 5 to 4 to 3 to 1 and eventually to 0 volts. Okay? That's the whole idea. Now, the question is how do we force this to 0 volts? Okay? Well, there's two things affecting this voltage in the middle. You have your source voltage right here. So you have Vs. The current will go through a resistor and go to V1. Okay, so realistically, if this is 5 volts for Vs, this V1 is probably going to be less, right? Because this is a source. And the voltage drop is based on the current and the resistance of this resistor. Okay? We could draw a very simple node equation right here, where we know V1, this voltage in the middle, is equal to Vs minus the voltage drop across the resistor. So we're going to have source voltage Vs minus R times I, which is a voltage drop across the resistor. That's how we find V1 in regards to the source. Okay. So remember, the op amp is going to force V1 to be 0 volts. That's what the op amp wants to do. So if this is 0 volts, how can we calculate the V out? Well, look at this resistor right here. If I know V1 is 0 volts, there's going to be current flowing through the resistor, so V out will be lower voltage than V1, right? And the difference is going to be this RF. So we could write another equation where we have 0 volts. V1, 0 volts is equal to Vs minus Rs times Is. Oh, I'm sorry, I'm just saying the same thing right here. Okay. I think this is the next page we'll talk about that. All right, so we know that the output voltages need to be 0. We just talked about that. Okay. How do we ensure that these two voltages are 0? Well, I could just look at the source current, source voltage, figure out the amount of current is needed to make this a 0 volts. That's easy. If this is 5 volts, this is 0 volts. I just do basic Ohm's law across the resistor. Okay, so again, Vn and Vp, these two voltages right here, will eventually be 0 volts. That's the rule of that's what the op amp wants to do. I have a source voltage that's constant, so there will be a constant amount of current flowing through Rs. Okay. And then this current will flow, it won't flow into the op amp, it has to go out through Rf to the output voltage. Okay. So this current will flow through Rs and through Rf to the output voltage, and this V out will change to ensure that this current will flow steady through the circuit. Okay, so remember that Vs is constant, current's going to flow, the 0 volt is kind of the anchor of the circuit, and the V out will change and do whatever it can to make sure the rest of the circuit stabilizes at 0 volts right here. That's pretty much how op amp works. Okay. You can kind of see it right here. Notice I'm trying to make the circuit simpler by taking off the op amp. When we take out the op amp, the circuit looks a lot smaller. Remember, we just said that this point right here, which is this point, the negative terminal right here, we need to pin that to 0 volts. So to my imagination, when I think of the circuit, I say this is going to be 0 volts. That's going to be the end of the rule forever. Okay. I know my voltage coming in. I know my current flowing through RS. I could calculate that. 0 volts equals VS minus RS times IS. Okay. And then now that I know the current flowing through RS, there's nowhere else for the current to flow. It's going to have to flow through RF as well. So the current's going to be the same across the whole circuit right here. So if this is 0 volts and I know the current flowing through RF, I can calculate V out through the voltage drop across RF. So V out is going to be RF times IF plus 0 volts. I didn't write the 0 volts, but it's there. Okay. I like to think about this circuit kind of like a seesaw, where 0 volts is the point, is a fulcrum that doesn't change. And then you have a positive voltage up here on the source. We're going to have a 5 volts, let's say here. We're going to grab a voltage drop across the resistor to 0 volts. And then the RF is going to be another voltage drop to V out to ensure that this stays at 0 volts. So it's kind of a lever that we move. If VS gets higher and moves up in voltage, V out needs to go lower and lower to stabilize at 0 volts. So it's kind of a seesaw that happens. Okay. So that's pretty much how inverting op amps work. The key component is just to make sure that the circuit stays at 0 volts, right? So putting everything back into place, this has to be 0 volts right here. We got current flowing through. There's going to be voltage drop. We're going to figure out how much current flows through. It's going to go through RF, and then V out is going to be some voltage based on the current through RF. Okay. Now, we don't have to go through this circuit every single time to figure it out. It's 2 voltage drop calculations. They summarize this as that the gain of the circuit, the output voltage compared to input voltage, is always a negative RF over RS. Okay. Now, one thing to note is notice if RF is bigger, the voltage gets lower faster. And the reasoning why is we're going to have the same current flowing through. If RF gets bigger with the same current flowing through, we're going to have a bigger voltage drop across the resistor, and V out is going to be more negative to make up the fact. Think about it right here. You see how we have these levers? If RF is twice as long as RS, this is literally longer plank right here. When VS goes up, RF has to go even lower, bigger, even lower and lower and lower voltage. So the longer and the higher we make RF, the lower the voltage, the more the gain we're going to have. And that's kind of like the back and forth play we get to do. So either if you want to increase in gain, you just make this RF resistor bigger, or you make RS smaller. One of those two. Okay. But whatever ratio you choose, this is the gain of the circuit. And again, notice it's negative, so whatever input voltage comes in, it's going to be negative on the output. So if I put 5 volts in and my gain is 10, my output is going to be negative 50 volts. Okay. Here's kind of an example to show number crunching, see everything happen. So remember, we have this voltage source. We know RS right here is 1 kilo ohms. We know RF is 3 kilo ohms. Let's look at a current flowing through the circuit, see how it flows through RS, and it flows through RF and it ends out in V out. Let's see what V out is going to be to force the whole circuit to 0 volts right here. Well, the first thing I would always do is calculate the current flowing through. I know VS, that's 5 volts right here. I know the negative terminal of the op amp needs to be 0 volts. I can do Ohm's law across RS. So current is equal to the voltage difference over the resistor, which is 5 volts over 0 volts over 1 kilo ohm, so it's 5 milliamps. So I know the whole green path right here is 5 milliamps flowing through the whole thing. Okay. Now, because I know 5 milliamps is flowing through RF, and I know it's 0 volts initially, I can then figure out V out pretty easily. That's again a voltage drop. So we have 0 volts minus I times RF is V out. Okay. So let's calculate the voltage drop across the resistor first, RF. Right here is positive, negative. It's just a current times RF. Well, we know that current flowing the whole circuit is 5 milliamps. We just figured it out previously. So 5 milliamps times 3 kilo ohms is 15 volts. So there's a 15 volt drop across RF. Now V out is going to be 0 volts minus RF because the current is flowing through 0 volts to V out. V out is going to be negative voltage. That's lower on the hill. So technically current's going to flow from 0 volts down to negative something volts. Okay. So our V out is going to be 0 volts minus, right here, 0 volts minus the voltage draw across the resistor. So 0 minus delta V, which is 15 volts, is going to be negative 15 volts. So your output is actually negative 15 volts. That way, the whole circuit is, you got 5 volts coming in, you got 0 volts here, you got negative 15 volts here. You see how current's flowing downhill the whole time, right? And the output V out, the V out was forced to change to negative 15 volts to ensure that the current flows through the whole circuit. Okay. Now, if we have an input of 5 and an output of negative 15, that means our gain is negative 3 for this op amp. We could back calculate it with and check with the math. We know V out over VS, V output over source voltage is negative RF over RS. Negative RF is negative 3 kilo ohms, so we get negative 3K divided by 1K, that's a negative 3 gain as well. So our circuit analysis proved true, and we just double checked it with the math, and there's also negative 3 gain, so everything works out. Okay, so this is how we calculate an inverting op amp. Now, that was engineering 17 review. Let's go to 117 now. How are we going to use that in today's world for our filter? Well, people got really smart and said, we could just manipulate the resistors with a capacitor to create a filter. So for RF, the feedback filter, let's put a capacitor in parallel. And we know from previously, if we put a capacitor and a resistor nearby each other, we can get a low pass filter. Okay, and having a capacitor and resistor right here in parallel is our filtering component, or low pass filter. So the overall gain of this circuit is going to be the same, negative R2 over R1. So it's just, they use R2 and R1 instead of RF and RS. So it's just same equation, just different notation. So the overall gain of the circuit is always going to be negative R2 over R1. But we're also going to tack on a low filtering component as well. So at a high frequency, this filtering part will go to 0 and it'll kind of cancel out the circuit. Right? So low pass filter means a low frequency. This will be equal to roughly 1 to let the whole circuit through. At a higher frequency, this will tend to 0 to kill the output. Okay. So remember, low pass filter is always omega C over S plus omega C, where omega C is always at cutoff frequency of 1 over R2 times C. This is the R2 resistant capacitor. We could tune the low pass filter for an exact cutoff point where we say this is pass band and this is block. Okay. So I always like to look at frequency, high frequency, low frequency in the circuit to see, make sure everything works out correctly. So let's ask ourselves, what happens at low frequency responses? Let's say we have a very, very low frequency. What happens to the circuit? Well, remember, capacitors at low frequencies are open circuit, right? They're not going to let current through. So if we have an open circuit in parallel with R2, what is going to be our total resistance? Well, RF equal R2 parallel infinite resistance is just going to be R2 right here, right? It's just, at the end of the day, the capacitor is just not helping it, so we just ignore it. So then at this point, the gain is literally just negative R2 over R1. This is your standard op amp gain. So the capacitor isn't doing anything in the circuit. It's like it's not there. But that's what we want. It's a low pass filter. We want to let the low frequency signals through like nothing happened. Okay. What about in the mid-range frequency where we're getting to that cutoff point? It's going to start creeping down a little bit. Well, at this point, it's R2 parallel with 1 over SC. Okay, because remember, we're doing frequency selection. We need to do the Laplace transforms and do a circuit analysis in Laplace. So R2 parallel 1 over SC, you're going to take RF, plug in R2 parallel 1 over SC, and then you're going to get this. The gain is going to be, again, your standard op amp gain, but the filtering effect will come in. And as the frequency gets higher, this will get lower and lower and lower, and then you'll eventually attenuate and the signal would disappear at high frequency. Okay, so this is kind of mid-range where you'd expect the filter to start activating and kind of filtering things out. Okay. Now, at the very high frequency, this is where we assume that the filter just blocks everything. Let's analyze what's happening in the circuit, right? Well, what happens to the capacitor at a high frequency? It's a short circuit, right? It shorts out. So what happens when you have R2 in parallel with a short circuit? What's the impedance of this whole system? Well, it's zero, right? Current's going to take a short circuit over resistor any day of the week. Okay. So the capacitor short circuit, what's the gain? Well, if R2 goes to zero, the gain's zero. Nothing else matters, right? And so at high frequency, the signal's gone. We killed it. Well, that's exactly what we wanted. You see? So by putting a capacitor there, we're able to manipulate the op amp to now be frequency sensitive. And we could change the capacitor to tune the low pass filter to whatever frequency we want to start attenuating and filtering out the high frequency signal. Okay. So overall put together, active low pass filter is an inverting op amp with a capacitor in parallel with the feedback resistor R2. The gain of the circuit has two components. It's always going to have the traditional op amp gain of negative R2 over R1. This is your standard gain. And the low pass filter will come into effect is omega C divided by S plus omega C. Okay. Well, omega C is 1 over R2 times the capacity. Okay. And just remember S, you plug in JW, or J omega, where omega is the frequency of the source at that particular band you're looking at. Okay. Let's kind of do an example real quick just to see the numbers. So let's say we have R1 is 2 kilo ohms. I want my cutoff frequency to be 1,000 radians per second. I want my gain to be -8. So how can you figure this out? Notice we have 3 components we need to analyze now and calculate. Okay. I already got R1, but we need R2 and capacitors. We need 2 things. Well, because we know the gain is -8, we could just say the amplification gain is equal to negative R2 over R1. We know gain needs to be -8 equals negative R2 over 2K. We could just say R2 is 16 kilo ohms. Okay, so there you go. That's the easiest part right there. So now we know R2 is 16 kilo ohms. That's the gain stage. Let's do the filtering stage. We know the cutoff frequency is 1 over R2 times C. So we got 1,000 radians per second is equal to 1 over 16K times capacitance. We just do some basic algebra, and capacitance is equal to capacitance is equal to 62.5 nanofarads. So now you know, you just go in the bin and get a 16 kilo ohm resistor right here. You get 62.5 nanofarad capacitor there, and boom, now you have your low pass filter, active low pass filter. And the gain's gonna be -8 every time. So that means if we put in -10 volts here and it's a very low frequency, we're gonna get -80 in the output. I'm sorry, if we put a positive 10 volts on the input, we're going to get a -80 volts on the output. Okay. If it's very, very high frequency, we're going to put 10 volts in and we can get 0 volts out. Okay. And so that's a good example to show. I want everybody now to sit down, take a 15-20 minute break, and you do a design example. Right here, we have an exact exercise. I have R1 is given as 2 kilo ohms. I know my frequency is set to 5,000 radians per second. That's my filtering point, my cutoff frequency. I want my gain to be -10. Follow what we just did. Figure out R2 and capacitor right here. Right here. Okay. That's the first part. Second part, I want you to figure out what's the gain of the circuit at omega equals 5,000 radians per second. So remember, you're going to have your gain of the circuit. You're going to have the S. Plug in S is equal to J omega, where omega is 5,000 radians per second. Find the magnitude of the gain. This is very, very similar to what we did in the passive filters from last week. You just have a gain, you just have the op amp added into it. Okay. So try and push it a little past what we normally cover. See what you can get out of this. We'll come back and we'll review your answers and see what you did. Okay. So see you guys back in, let's say, 15-20 minutes. Okay. Good luck. All right, hello, welcome back to EEE 117, chapter 15, active filter circuits. So here we had our exercise real quick to check out an active low pass filter. So here's kind of what we should gotten. So remember, R1 is 2K, cutoff frequency, we want to design it for 5,000 rads per second. Our gain should be negative 10, negative 10. So first thing I always typically do is look at the amplification stage. We know our gain needs to be negative 10. We need to find R2. We know R1 is 2 kilo ohms, so it's just basic, algebra. R2 is equal to 20 kilo ohms. And then we have our cutoff frequency of 5,000 rads per second. So we have 5,000 equal to 1 over R2 times C. We know R2 is 20K. We need to find C, just some basic arithmetic, and we can figure out what capacitor is 10 nanofarads. So basically, R2, 20,000 kilo ohms, capacitor 10 nanofarads, and we have our active low pass filter. Let's do some analysis and make sure that it works as intended. So what's the gain of the circuit? Now, I'll set the magnitude just to make things a little easier, is V out over V in, that's the gain of the circuit. Take your magnitude. Remember, the gain is equal to the amplification stage of negative R2 over R1 times the filtering stage, omega C over S plus omega C, right? Omega C is a cutoff frequency. That's already 5,000 rads per second. So we just go 5,000 here, 5,000 there. A frequency we're trying to look at is also at 5,000 rads per second, so it's right on the cutoff frequency. So S, we can plug in this J omega, where J is J 5,000. The gain stage is R2 is 20K. We've calculated that, so it's 20 over 2K, which is R1. So we get the gain is negative 10 for the gain amplification stage. The filtering stage is 1 over square root 2. So then our total gain circuit is 7.07, or about the gain is roughly of 7, the magnitude is, right? So notice that it's not 10 anymore. It went down to 7, because right at the cutoff frequency, remember the gain started going down a little bit because it started to veer down. So the cutoff frequency is kind of like the middle area where we're on that threshold on and off. And it's roughly about 70% of the original power is when it turns off. That's why you have the 1 over square root 2 for the filtering stage. That's 70% power. But then we multiply by 1,000% because 10, right? That's 1,000% gain. So then our total gain is about 700%, or a gain of 7. Okay. Honestly, the inverting part isn't that big of a deal in today's world, because honestly, if this is negative voltage, the easiest thing we can do to change that is you just cross the wires to the next phase, right? So if the gain is negative 7, we just flip the wires to the next circuit and magically it becomes positive 7 again. Right? So the inverting part's not that big of a deal. I just want to show you that it's really good to test your circuit, to plug in a specific frequency to see what's happening. Remember, when we go to the lab and you look at the oscilloscopes, you can do a frequency sweep. It'll literally take the source right here, which is your function generator. And when you do frequency sweep, it'll literally plug in. This source will go from omega equals 100, 200, 300, 400, 1,000, 2,000, 3,000, all the way to like 10,000 or 50,000, whatever you choose. It's going to literally go through and check the frequency and the output of each part, and then you'll get that Bode plot at the end. All right, and you can have a Bode plot for this just as much as anything else. Okay, so very similar to the passive filters, except we just that additional gain stage of negative R2 over R1 added on. Okay, so that's active low pass filter. Another popular thing we need to look at is a high pass filter. So remember, high pass filter is we're only letting high frequencies through or blocking low frequency. So how do we do that? Well, we still need to do our inverted op amp, except this time we're going to put a resistor in series with R1. So we're going to start manipulating R1 instead of R2 to get that high frequency signal through. Okay. So the gain of this circuit will now be R2 over R1. Technically, this should be negative. So let's put a negative right here. Negative R2 over R1. And that's your standard op amp gain. And then we're multiplied by the high pass filter stage. Remember, high pass filter is going to be S over S plus omega C, where omega C is the cutoff frequency. Okay. Now, again, let's look at low frequency. What's the circuit do before even doing any math? At low frequency, we know the circuit is open, capacitor is open circuit at very, very low frequencies. So that pretty much kills the circuit. It kills the input right there. If I have 5 volts and this is an open circuit, my op amps are going to see 0 volts. So the rest of the circuit is dead. But that's what we want. It's a high pass filter. High pass means low frequency should be cut off completely, which we cut it off by the capacitor right here, right? We could look at the math. The gain of the circuit is R2 over R1 plus 1 over SC. right? And this gain, we just multiply everything through, is going to be 0. Right? So very, very easy. Low pass filter for mid-range. At the mid-range area, this capacitor is going to kind of start letting things through. It kind of starts blocking. It's kind of half and half area, right? This is where the gain is negative R2 over R1 times S times over S plus omega C, right? Well, omega C itself is the cutoff frequency. That should be multiplied right there. Okay. All right, and because they're both in series, the voltage will have to pass. The voltage is going to get dropped by both of these, so capacitors can have a small voltage drop, so the gain will be there. Okay. Now, what about very, very high frequency? Now, remember, this is where we want to let the circuit through. At high frequency, the capacitor shorts out. So this is a short circuit. We just kind of ignore the capacitor. This is just a basic op amp from Engineering 17. It's just R2 over R1 gain. So notice the gain is negative R2 over R1 plus 1 over SC. What happens when we have infinite impedance, infinite frequency? Well, the S becomes infinity. We have negative R2 over R1 plus 1 over infinity, which is 0. So it kind of goes away. Right? So mathematically, your gain is just negative R2 over R1, which is just your standard gain of op amp. And, at this point, it's like the filter's not even there, which is what you want. At high frequencies, the filter should be invisible to the signal. Okay. So that's your high pass filter. Let's go ahead and put it all together. So just remember, you put a capacitor in series or R1. The output, the gain of the whole circuit is going to be negative R2 over R1. This is your amplification stage. You multiply by your filtering stage, which is S over S plus omega C. Omega C is 1 over R1 times C. Notice it's R1 and not R2. Omega C is the cutoff frequency will always be relative to the resistor next to the capacitor. So right here, because this resistor and this capacitor is literally right next to each other, these two are going to be the ones involved with the cutoff frequency. R2 has nothing to do with the cutoff frequency in this particular one. Okay. All right, let's go ahead and do a quick number crunch to see what happens whenever we design some stuff. So we have this active high pass filter going on. We have the gain where we need to find it as -8. So the gain's right here, -8. We have R1 is equal to 2 kiloohms, and our cutoff frequency is 1,000 radians per second. So always two ways you can do this. I like to go ahead and start with the gain right here, where you have a gain is equal to negative R2 over R1. We know the gain is -8. That's what's asked. -8 is equal to negative R2 over 2 kiloohms. R1 is already given to us. There's no current at. R2 is equal to 16 kiloohms. So that's R2 up here, right? The cutoff frequency, omega C, is equal to 1 over R1 times C. R1 specifically because remember capacitor right next to the R1 resistor, right? Omega C is 1,000 radians per second. That's asked for us. That's equal to 1 over 2K times C. C needs to be just no crunches around, 0.5 microfarads. Right? So very similar design. Just you gotta just make sure you're using R1 instead of R2 for the cutoff frequency. Okay. So everything put together, here's kind of a summary of the low pass and high pass filters, active filters. So active low pass filter will always have the capacitor in parallel of R2. Notice the gain is negative R2 over R1. That's the standard amplification stage, where the low pass filter will be omega C over S times plus omega C. That's the low pass filtering stage as well. So you have a standard amplification stage and a low pass stage, filtering stage. You could design circuits where your cutoff frequency is always going to be 1 over R2 times C for the low pass filter. Active high pass filter has a very similar but slightly different architecture. So this time the capacitor is in series with R1, and the gain is now negative R2 over R1. This is your amplification stage. You multiply it by the high pass filtering stage of S over S plus omega C. Okay. Or omega C is 1 over R1 times C. Notice R1 because the resistor is next to the R1 is next to the capacitor. Okay. So very similar, slight, very, very small tweaks to the design. But overall, this is very, very a good foundation building block of designing the active low pass filter and the active high pass filter. Right. In the future, you'll probably learn more advanced techniques and do multiple stages of this to get better and better results. but this is the building blocks of everything, okay? So I want to say thank you for showing up and watching this video and learning a little bit about some active filters. We're going to come back on later on in the week, talk about bandpass and band reject filters, the active bandpass and active band reject filters, to see how they're designed as well. Okay. So thanks for showing up. Hope everybody has a good day, and we'll catch you next time. See you around.